Okay, yaar. So good afternoon here. Good afternoon everyone. Okay. Okay. So we are going to start the lecture here. We are going to start the lecture. Okay. So in the previous session here, I have explained about Lorentz force equation for B field, right? Lorentz force equation for B field. So what I have told here, Lorentz force equation for B field, that is nothing but, see, whenever a charge is present, a stationary charge is present in magnetic field, it is not going to experience any force. Whereas if the charge starts moving here, in a B field, then it is going to experience what? It is going to experience a force, right? Okay. So that's what we have seen yesterday. So what I have given is Lorentz force equation here. Lorentz force equation for B field is equal to what? What we got? Q into what? Q into V bar cross B bar. V bar cross B bar. So whenever you are having a charge moving with velocity V kept in magnetic field B, it is going to experience a magnetic force F, right? Yes or no? Okay. So this is called as Lorentz force equation for B field. And also I have said that Lorentz force equation for electric field here, that is F is equal to what? F is equal to EQ. F is equal to EQ. Right. Okay. So this is the Lorentz force equation for electric field, and this is the Lorentz force equation for B field. So yesterday we have also seen that, in the previous session we have seen that the direction of electric field and the direction of electric force both are going to point in the same direction, whereas the direction of magnetic force here and the direction of B field here both are perpendicular to one another. So all these things we have seen. Okay. So this is the Lorentz force equation for B field, this is the Lorentz force equation for electric field. So if you are having both the fields here, then the Lorentz force equation will become what? You are having both B field as well as what? Electric field. So the Lorentz force equation will become the combination of these two. So that means you have to write now here EQ plus Q into what? Q into V bar cross what? V bar cross B bar. Yes or no? Okay. When you have to write this equation here, whenever you are having both electric field and magnetic field. So this is the general Lorentz force equation here. Okay. So if you deal with only B field, then you should not consider this one, you have to consider only this one. So whenever we are dealing with electric field, you have to consider only this one but not this one. Right. Okay. So if you are dealing with both the fields, then you have to consider both the equations. You have to write both the terms. Okay, so this is the generalized Lorentz force equation. This is called as what here? Generalized Lorentz force equation. So this is general form of Lorentz force equation here. Lorentz force equation. General form of Lorentz force equation. Okay. Okay. So now see here, they have asked you a question here in IES. They have asked this question, direct question. See, in IES they have asked this question here. See, direct question here. What they are asking? Lorentz force law for point charge Q is given by. Lorentz force law for point charge Q is given by. A direct question here. Yes or no? So which one is correct answer here? Which one is correct? F is equal to what? Q into E plus V bar cross B bar. So this option is correct. Yes or no? So remaining all other options are wrong. So in this manner they will give direct questions here. They will give almost direct questions and conceptual questions in engineering services examination. Right? Okay. Okay. Yeah. So this is one of the simple questions that they have given here based on Lorentz force equation. Next here. Next. So today we are going to start a new topic here. We are going to start a new topic, that is Biot and Savart's law. That is Biot and Savart's law. That is Biot and Savart's law. See, what is this Biot and Savart's law means? It is going to tell you how to determine a small differential B field at a point at a distance r from a small differential current element. That means if suppose if you are having a small differential current element, okay, it is going to produce a small differential B field. So what is the B field it is going to produce? If you are having a small differential current element, what is the small differential B field it is going to produce? So that is given by Biot and Savart's law. Okay, so now see here. Now if suppose if you are having a current carrying wire here, you are having a current carrying wire like this. Let us say this is current carrying wire. So it is carrying a current I. It is carrying a current I. Okay. Okay. So now if you consider a small differential current element, I am considering a small differential current element here. A small differential current element. So a small differential current element, current is flowing in this direction. So I can represent this as IDL bar, right? IDL bar. So IDL bar represents a small differential current element. This one here, a small differential current element. So now due to this one, if you want to determine the B field, if you want to determine the B field somewhere here, if you want to determine the B field at this location. So since it is a small differential current element, the B field produced by this small differential current element will consider as a small differential B field, a small differential B field. So we want to determine this one here. We want to determine this one. Right. Okay. Okay. And the angle between these two, the angle between this IDL bar, this current element, and this one here, this one. See, this is the distance from the current element to this point is nothing but r here. The distance between the current element to this point is nothing but r. Okay, so r into AR cap I can represent. This is a vector quantity or not? This is a vector quantity. So I am representing r is magnitude and AR cap is the unit vector that is going to give you the direction. See, always this r bar here. So you can represent the same thing as r bar also, right? Okay, so always this r bar must point from the current element to the point where you are trying to determine the B field. It has to always point in which direction here? This r bar must always point from the current element to the point where you are trying to determine the B field. It always points in this direction here. Okay, so remember this point. Okay, so the B field produced by this small differential current element is given by Biot and Savart's law. Biot and Savart's law. So what this law says is the small differential B field, dB is directly proportional to this current element, that is IDL bar, this current element. IDL bar, and inversely proportional to the distance between the current element and to the point where you are trying to find out the B field. The distance between the current element and to the point where you are trying to determine the B field. Okay, so it is inversely proportional to square of the distance between current element and this point, right? Okay. And here you are going to do the cross product with what? With unit vector along r. So that means unit vector is going to point in which direction? Unit vector is pointing in this direction here. This is AR cap direction, right? So unit vector is pointing along r in this direction. It always points from the current element to the point where you are trying to determine the B field. This is very important here. Remember this. Okay. Okay. Okay, yeah. So now here dB is equal to, so this is proportionality here, it is proportional to this current element and inversely proportional to square of the distance. So whenever you are putting equality, you have to add, include proportionality constant here. So here the proportionality constant is nothing but mu by 4 pi. Here the proportionality constant is nothing but mu by 4 pi. So mu by 4 pi into IDL bar cross AR cap divided by r square. So this is the differential B field produced by what? Produced by a small differential current element IDL bar. So this is the expression for the B field, a small differential B field produced by a small differential current element at a distance r. So this is called as what? This is called as Biot and Savart's law. This is called as what here? Biot and Savart's law. Okay. Okay, yeah. Now see here. Okay. Okay, yeah, fine. See, what is the purpose? What is the purpose of this Byert-Savart's law? What is the purpose of this Byert-Savart's law? See, we can determine, if you are able to determine here, if we are able to determine the B field due to a small differential current element, then if you want to determine the B field due to this total current element here, then you can determine that or not. Yes or no? So that means if you integrate throughout this length of the current carrying wire, then you can determine the total B field. So if you know the B field due to a small differential current element, then by integrating that, you can determine what? You can determine the B field due to a current element of any length. Yes or no? So that is the advantage of this Byert-Savart's law. That is the advantage of this Byert-Savart's law. Now one more thing here I want to specify here is, see here. Now see here I have written AR cap here, AR cap. Okay, so AR cap is pointing in this direction, Now AR cap, this AR cap is neither parallel to IDL bar, yes or no, that is current element. It is neither parallel to this current element nor perpendicular to this current element. So this AR cap is neither parallel to this current element nor perpendicular to this current element. So I can resolve this into two components. One is what here? One is along the current element, and another one is what? Another one is perpendicular to what? Perpendicular to current element. So I can resolve this AR cap into two components. One is perpendicular to current element, and another one is what? Another one is parallel to what? Parallel to current element, and perpendicular to current element. In this manner I can resolve, right? Okay, so the component that is parallel to current element, so this one and this one both are same or not? Yes or no? Yes or no here? This one and this one both are same. So what is the component of AR cap along the current element direction here? That is nothing but what? That is nothing but cos alpha, right? That is nothing but cos alpha. Yes or no? AR cap, this is AR cap here, yes or no? Okay, so what is the component of AR cap along this direction? That is nothing but cos alpha. What is the component of AR cap along this perpendicular direction? That is nothing but sin alpha, right? Okay, so let us consider it is the current is flowing along x direction. Let us consider the current is flowing along x direction, and let us consider here it is y direction. Okay, so now this cos alpha, this component, this is the component of AR cap here. This is the component of AR cap along x, and component of AR cap along y is nothing but sin alpha. So I can represent this AR cap. As cos alpha AX cap plus what? Plus sin alpha AY cap. Yes or no here? AR cap I can represent as cos alpha AX cap plus sin alpha AY cap. So if you substitute this here, in the above expression, what you are going to get? dB bar is equal to what? Is equal to mu into I dl. See this dl bar, this is the differential length along which axis here? Along which axis we have considered? Along x direction or not? So I can replace this dl bar. With what here? With dx ax cap. This is because this is the differential element that is present along what? Along x direction. So I can represent this as dx ax cap, right? Okay, yeah. So mu into I dl I can represent as dx ax cap cross. So here I can write cos alpha ax cap plus what? Plus sin alpha ay cap. Cos alpha ay cap plus cos alpha ax cap plus sin alpha ay cap. Divided by what? Divided by 4 pi r square. So if you do this, what you are going to get here? dB bar is equal to what? Mu into I dx by 4 pi r square, 4 pi r square. Now here ax cap cross ax cap here, ax cap cross ax cap will become what? Will become 0, right? And ax cap cross ay cap will become what? Will become az cap, will become az cap. Yes or no? Okay, will become az cap. So what you are going to get? Ax cap cross ax cap, you will get 0, and ax cap cross ay cap, you will get what? You will get plus sin alpha into az cap, az cap. So that means you are going to get, therefore dB bar, you can write it as what here finally? Wait here. So dB bar, you can finally write it as mu into I dx by 4 pi r square into sine alpha az cap, sine alpha into az cap. So in this manner you can write here, in this manner you can write. So here this is now the direction of B field is pointing in which direction here? Az cap direction. See here, see here, see the current is flowing, the current is flowing in this direction, the current is flowing in this direction. Here I have considered x-axis, in this direction I am having x-axis, in this direction I am having y-axis. So what is the direction of positive z-axis here? What is the direction of positive z-axis? What I have said here, what I have said, so always you have to curl your right hand fingers from x to what? From x to y. So if you curl your right hand fingers from x to y, the thumb is pointing into the board. That means the positive z direction, the positive z axis must point what? Must point into the board, into the board, right? Okay, so this is how we have considered the axis here. Now here the current is flowing in upward direction here, the current is flowing in upward direction, right? So whenever the current is flowing in upward direction, what is the direction of B field at this location? At this location, what is the direction here? See, point the thumb along what? Along current direction, point the thumb along current direction, then enclose your fingers like, enclose your fingers here, okay, enclose your fingers like this. So if you enclose your fingers like this, this is going to give you what? This direction is going to give you what? The direction of the B field, the direction of the B field around this current carrying wire. Okay, so if the current is flowing like this, means at this location the B field is pointing into the board. Yes or no? The B field is pointing here, it is pointing into the board, and here it is coming out of the board. So the loops are going to form like this. Yes or no? Yes or no? Okay, so that means here the B field is going to point into the board. Here the B field is going to point into the board, right? Okay, so into the board means which direction here? Into the board means it is pointing in positive z direction. Into the board means it must be in positive z direction. So that's what we have got here or not? Yes or no? See what we got. The direction of B field, the direction of B field is in positive z direction. That's what we got. Yes or no here? Okay. Okay here. See one thing remember here, one thing remember. See from this expression, one thing remember. See here, you are having dB bar is equal to mu I dl bar cross AR cap, mu I dl bar cross AR cap divided by what? Divided by 4 pi r square. You are having this expression or not? See here, always the direction of this B field here, the direction of this B field must be what? Must be perpendicular to what? Must be perpendicular to both this DL bar and AR cap. Yes or no here? See, you are doing the cross product between these two. So whenever you are doing the cross product between these two here, between the current element and AR cap must always point in which direction? Always point from the current element to the point where you are trying to determine the B field, right? Okay, so if you do the cross product between these two, okay, so what is the direction here? What is the direction you are going to get? The direction must be always perpendicular to what? Perpendicular to the plane containing this both current element and AR cap. So that means the direction of B field here, the direction of B field must be always what? Must be always perpendicular to the plane containing what? Containing the current element and AR cap, right? Okay, so in this manner you can remember the direction here. So always here, always the direction of B field, always the direction of B field must be what here? Always the direction of B field must be wait here, always the direction of B field must be perpendicular to the plane, perpendicular to the plane containing, perpendicular to the plane containing both ideal bar and AR cap, ideal bar and AR cap, right? Okay, so it must be always perpendicular to both a plane containing both ideal bar and AR cap. Okay, okay, yeah. So always the B field direction must be perpendicular to the plane containing both ideal bar and AR cap. So this point is very, very important here. This point is very, very important. That means what? B field must be always perpendicular to what? Perpendicular to the current element. So whenever you see a current element, B field must be what? B field must be perpendicular to that current element. See here, if you observe here also, the current is flowing like this. So the B field is going to circulate like this. Yes or no? The B field is going to circulate like this. So that means B field is present in which plane here? B field is present in which plane? B field is present in YZ plane, right? Yes or no? And the current is flowing in X direction, right? So that means the current element direction and the B field direction, both are what? Both are perpendicular to one another, right? So these are the conclusions that we can get from this Biot-Savart's law. Okay, so these are the very, very important points that you have to understand and observe from this Biot-Savart's law. So make all these points here. Make a note of all these points. Okay, okay, here. So is it clear here? Is it clear? Okay. So I hope it is clear here. I hope it is clear. Next here. Next. See. So what I said here. What is the application of Biot-Savart's law? If you are able to determine the B field due to a small differential current element, then you can easily determine the B field due to a large current element also by integrating throughout the length. Yes or no? Okay. So we are going to do that. We are going to do that now. Okay. See here. Now here, let us consider. Okay. So now let us consider a current carrying wire here. Let us consider a current carrying wire. Okay, let us consider a current carrying wire like this. Oh. Okay. Okay, let us consider a current carrying wire like this. So now here the current is flowing. Here the current is flowing in this direction. The current is flowing in this direction. Now let us assume this axis is Z axis here. Let us assume this axis is Z axis. Okay. And this is, let us say, origin. Let us say this is origin 0, 0, 0. Now here okay, so now we want to determine the B field at this location here. We want to determine B field at this point P. We want to determine the B field at this point P. So due to this current carrying wire, okay. So how we can do that? See here. Let us assume the length, this end of the wire I am representing with A, and this end of the wire I am representing with B. This end of the wire I am representing with B. Right. Okay. So this is the current carrying wire. So now due to this current carrying wire, of length AB, I can say of length AB. Okay, so due to this length, this total length of the current carrying wire, what is the B field at this location? What is the B field at this point? Okay, so that's what we want to determine here. That's what we want to determine. Now let us consider let us consider a small differential. I am applying what? I am applying simply Biot and Sever's law, right? Okay, so I am considering a small differential current element here, I d L bar. So dl is nothing but what? It is along z direction, so I can represent simply I dz az cap, right? So this dz az cap in general will represent with what? Dl bar. So here this dl bar is along z direction, so I am representing that dl bar with what here? With dz az cap, with dz az cap, right? Okay, okay, yeah. So now this small current element is subtending an angle at this location. It is subtending an angle. This is nothing but what? The distance from the current element to the point where you are trying to find out the B field. So this is nothing but what? This is nothing but R bar. Yes or no? That is R into AR cap. R into AR cap. Right? Okay. Next, see here. So this angle here, this angle I am considering as alpha. This angle I am considering as alpha. So here I am going to consider the angle here throughout this derivation. I am going to consider the angle. Always in anti-clockwise direction. Okay, so throughout this derivation I am going to consider the angle with respect to this current element and this line as what? In anti-clockwise direction. Okay. So whatever the result that we are going to get here, okay, so if you want to use that result in problems, there also you have to consider always the angle in anti-clockwise direction. So whatever the convention we are following here, okay, so the same convention you have to follow whenever you are solving the problems also. It is not mandatory to always take in anti-clockwise direction, you can take in clockwise direction also, but here we are following the convention that angle I am always considering here in anti-clockwise direction. That is the convention I am following, right? Okay, okay, yeah. So this is alpha, this is nothing but IDL AZ cap, and this is R. Now first I am going to determine a small differential B field at this location by using Biot and Sever's law. So we already know how to determine the small differential B field by using Biot and Sever's law due to this current carrying element, right? So what you are going to get? Tell me what you are going to get. So dB is equal to what? Just now we have seen, yes or no? dB is equal to mu by 4 pi I dl bar. Now here dl bar is nothing but what? Dz az cap. I dz az cap cross what? Cross AR cap. Divided by what? Divided by R square. Yes or no? Mu I dz az cap cross AR cap divided by 4 pi R square. So this is the small differential B field. Now see here. So dB is equal to mu by 4 pi R square. See, so mu by 4 pi I dz by R square, and here az cap cross AR cap. What is AR cap here? How you can write AR cap? Tell me. So now this is AR cap, this is alpha. Yes or no? So this AR cap is neither parallel to this current element nor perpendicular to this current element. This AR cap is neither parallel to this current element nor perpendicular to this current element. So I can resolve this AR cap into two components. Yes or no? Into two components. So one is this one, right? One is this one. Yes or no? And another one is this one. So another one is this one, this component and this component. See, like this. So this is AR cap you are having. So I am resolving this into two components. Like this. Yes or no? Okay. So this is z-axis we are having. And here the angle is nothing but what? Alpha. So what is this component here? This component is nothing but cos alpha. It is pointing in which direction? Downward direction. That means minus AZ cap direction. And this component is pointing in which direction? So let us consider this direction. We have not mentioned, na? Let us consider this direction as y direction here. Let us consider this direction as y direction, y axis. Okay, this is y axis, let us assume. So this component is nothing but what? Is nothing but sine alpha. It is pointing in which direction here? Y direction. Sine alpha ay cap. Sine alpha ay cap. Right. Okay. So AR cap is equal to cos alpha minus AZ cap plus sine alpha ay cap. Right. Yes or no? So this is nothing but AR cap. So substitute this here. What you are going to get? You are going to get cos alpha minus AZ cap plus sine alpha ay cap. So what you are going to get? Tell me. So mu I dz, AZ cap cross AZ cap will become 0. AZ cap cross AY cap will become what here? Is nothing but minus AX cap, right? So you are going to get here sine alpha minus AX cap, See, you can write directly here. Whenever you are having a cross product, AZ cap cross AR cap, you can write 1 into sine alpha directly. But you don't know the direction, na? You can write sine alpha, yes or no? But you have to get the direction, na? Here we are getting direction also or not? Yes or no? If you do this, you are going to get the direction also. We know that sine alpha will be present, yes or no? Okay, but we don't know the direction. In order to get the exact direction, I am writing AR cap in this form. Right, okay, so it is minus AX cap divided by what? Divided by 4 pi. Here, how I can write r square here? See here, see the distance from here to here I am considering as rho here, the distance from here to here. Okay, the distance from here to here. That means here rho represents what here? Rho represents the normal distance from the wire or not? So this is the wire and rho is the normal distance from the wire. Yes or no? Okay, so this is nothing but rho. See, this is r here, this is r. Now let us consider the distance from here to here. Let us consider the distance from here to here is z. The distance from here to here is z. The distance from here to here is r. The distance from here to here is, sorry, what I am saying here? The distance from here to here is rho. The distance from here to here is z. The distance from here to here is r. Right? Okay, so that means you are having like this here. So here z you are having, here you are having r, and here you are having rho, right? And here you are having angle alpha, here you are having angle alpha, right? So from here, from this right angle triangle here, from this right angle triangle, this is 90 degrees. So from this right angle triangle, what is r here? R I can write it as square root of what? Square root of rho square plus z square. I can write r is equal to square root of rho square plus z square. And one more thing, see here, see here. So here you are having r square here, r square. So substitute this r square will become what? You will get rho square plus what? Rho square plus z square, right? Rho square plus z square. Okay. So now see here. See here, so this is the small differential B field here. This is the small differential B field due to this small differential current element. Due to this small differential current element. Now I want the B field due to this total current element here. I want the B field due to this total current element. So what I have to do here? I have to integrate throughout the length of the current carrying wire. Throughout the length of the current carrying wire. That is from B to A. From B to A. So now if I consider at B here, at this end, if I consider a small differential current element. Okay, so then it is going to subtend some angle. It is going to subtend some angle at this point, right? Okay, let us say that is alpha 1. Let us say that is alpha 1. So it is subtending some angle at that point. So let us say that angle is alpha 1. What I have said here, always I am going to consider the angle. I am going to consider the angle in anti-clockwise direction. Okay, that has to be followed here. That is the convention we are following. And let us consider this end of the wire. This end of the wire is subtending an angle. This end of the wire is subtending an angle alpha 2. Let us say this end here, this end of the wire is subtending an angle alpha 2. This end of the wire is subtending an angle alpha 1. Okay, so now as you move from this end to this end here, as you move from, if you consider the small differential current element here, and if you move this current element here, and so on up to this end here. So as you move this current element, small differential current element from B to A, what is going to change? Alpha is going to change from alpha 1 to what? From alpha 1 to alpha 2. Yes or no? So that means if we want the total B field here, if you want the total B field, what you have to do? You have to integrate with respect to alpha, from alpha 1 to what? From alpha 1 to alpha 2. You have to integrate that small differential B field from where to where here? From alpha 1 to alpha 2. So if you move from alpha 1 to alpha 2, you are going to cover this total length of the wire. Yes or no? Okay. So that means here I'll try to express each and everything in terms of what? In terms of alpha. Then I'm going to do the integration with respect to alpha from where to where here? From alpha 1 to alpha 2. So then I'm going to get the total B field, right? Okay. So now here we are having here dz here. We are having here dz. I want to integrate with respect to alpha. That means I have to write this dz in terms of what? D alpha. So how we can do that? See here. See, from this right angle triangle here, what is rho by alpha here? What is rho by, or you can say in this manner, what is z by rho here? Z by rho. Z is adjacent side, rho is what? Rho is opposite side. So what you are going to get? Z by rho is nothing but what? Is equal to cot alpha. Z by rho is equal to cot alpha. So therefore Z is equal to what here? Z is equal to rho into cot alpha. So if you do this substitution here, Z equal to rho cot alpha in this expression, what you are going to get here? Here you are having dz also. Here you are having dz and here you are having z. In place of z you can substitute rho cot alpha. In place of dz, what you have to substitute? So in order to substitute in place of dz, what you have to do here? Differentiate. So what you are going to get? You are going to get dz by d alpha. Okay, dz by d alpha is equal to minus rho into cosecant square alpha. So I am sending d alpha to this side. So you are going to get dz is equal to minus rho into cosecant square alpha d alpha. So this is the value of what? This is the value of dz in terms of d alpha, and this is the value of z in terms of what? In terms of alpha. So if you substitute these two parameters, in our expression, you are going to get the expression everything in terms of what? In terms of alpha. So then you can integrate with respect to alpha from alpha 1 to alpha 2 in order to get the total B field here. Yes. Okay. Yeah. So now see here. So if you integrate here, I'm writing directly here. So if you integrate, you are going to get what? You are going to get the total B field. So you have to integrate from where to where? From alpha 1 to alpha 2. So mu into I sin alpha. Divided by 4 pi into rho square plus z is equal to what? Z is equal to rho cot alpha. So substitute that. Z equal to rho cot alpha, that is you will get rho square cot square alpha. So in place of z I have substituted rho cot alpha. Next here you are having minus ax cap. So in place of dz, what you have to substitute here? What we got? Minus rho cosecant square alpha d alpha. So substitute that here. So you are going to get minus rho cosecant square alpha d alpha, right? Okay. So this is equal to now here sin alpha, okay, minus rho cosecant square alpha sin alpha mu I by 4 pi rho square plus rho square cot square alpha. See, from this expression I can take rho square common here. You are going to get what? You are going to get 1 plus cot square alpha, and the value of 1 plus cot square alpha is nothing but what? Is nothing but cosecant square alpha. So that means here I can simply replace with what? Simply replace with rho square into cosecant square alpha. Okay. So what you are going to get here? Tell me. So integral alpha 1 to alpha 2 mu I sin alpha into minus rho cosecant square alpha d alpha minus ax cap here divided by 4 pi into rho square cosecant square alpha. So here cosecant square alpha will get cancelled. Here rho will get cancelled. Okay. So what is left out here? Take all the constant terms outside here. Mu is constant, I is constant, right? 4 pi is constant, rho is also constant. So take all these constant terms outside. So you are going to get mu I by 4 pi rho. Mu I by 4 pi rho. Next, what is left out here? Integral sine alpha. Integral sine alpha d alpha is nothing but what? Is nothing but minus cos alpha. Integral d alpha sine alpha is nothing but what? Minus cos alpha, right? Yes or no here? Okay. See, integral sine alpha is cos alpha or minus cos alpha here? Integral differentiate, okay, minus cos alpha. So minus cos alpha, its range is from alpha 1 to alpha 2. Alpha 1 to alpha 2. Okay. So wait here. Minus rho cosecant square alpha. Okay. Okay. So minus cos alpha, its range is from alpha 1 to alpha 2. Okay. So what you are going to get here? Mu I by 4 pi rho. So what you are going to get? You are going to get cos alpha 2 minus cos alpha 1, and here minus is present. So you can write cos alpha 1 minus cos alpha 2. So now here we got the B field is in direction minus AX cap. So this is the expression here. This is the expression for B field, right? Wait. Do we have done anything wrong here? Wait here, 1 minute here. So is there minus sign, plus sign? Everything is correct, or we have done somewhere wrong here? dz is minus rho cosecant square alpha d alpha, right? Okay. So 1 cosecant square alpha, okay, right? Cosecant square alpha, right? Okay. Okay, see here you are having minus now, here you are having minus. We have forgot this minus here. So if you take this minus outside here, minus outside, here you are going to get minus, right? So here minus will become what? Here minus will become plus. Then you are going to get what? You are going to get here cos alpha 2 minus what? Cos alpha 2 minus cos alpha 1, right? Okay, so this is the expression you are going to get here. So that is B field due to a current carrying wire. B field due to a current carrying wire of finite length is equal to what? Is equal to mu I by 4 pi rho into cos alpha 2 minus cos alpha 1. This represents minus AX cap will represent the direction of the B field. The direction of the B field. See here, the current is flowing in which direction here? The current here is flowing in Z direction, right? So the B field is going to curl like this, yes or no? So the B field is going to point like this. So at this location here, at this location on this side, it is going to point into the board. On this side, it will come out of the board. So here at this location also, it will point in which direction? The current is flowing like this. So at this location, it is going to point into the board. Into the board means which direction here? Minus AX cap direction or not? Yes or no? Negative X direction. So that's what we got here or not? Yes or no? So we got the direction of B field is in minus AX cap direction, right? Okay. So mu I by 4 pi rho into cos alpha 2 minus cos alpha 1. Okay. Okay here. Now see here, in general, what is the direction of B field? You can write here. What is the direction of B field? You can write. See, if you are having here, I write like this here. Here you are having current carrying wire. Okay. So the B field is going to point like this. Yes or no? It is in anti-clockwise direction like this. Yes or no? Okay. So the direction around this closed path here, the direction around this circular path, you can represent it as what? You can represent it as A phi cap or not? You can represent it as A phi cap, right? So in general, B field, B bar is equal to, you can represent as mu I by 4 pi rho into what? Into cos alpha 2 minus cos alpha 1 into what? Into A phi cap. and also I have explained here, I have explained in the previous classes how to represent this a phi cap in terms of ax cap, ay cap, like that. Yes or no? Okay, I have explained all these things. So if you substitute that, you are going to get here minus ax cap only. Understood? Okay, so you can do that later here. But in general, we can write the direction is what? A phi cap. If it is in clockwise direction here, if the field is circulating in clockwise direction, that means if the current is flowing in downward direction, then the field is going to circulate in clockwise direction here. If the field is circulating in clockwise direction, then instead of a phi cap, you can replace with what? You can replace with minus a phi cap. Right? Okay, here we have used simply rectangular coordinate system exactly at this point. Exactly at this point we are getting the direction as what? Minus ax cap. If you want the direction anywhere, then you can simply replace with what? A phi cap here. A phi cap. So this is the general expression. Right? Okay, so understood here? Understood? Yes or no here? Okay. Okay, yeah. So I hope it is clear here. So finally, what we got here? The B field due to a current carrying wire of finite length we got as B bar is equal to mu I by 4 pi rho into cos alpha 2 minus cos alpha 1 a phi cap. So it is general direction here. Generally we can represent in terms of a phi cap. Okay, because it is tracing what? It is tracing the circular path. B field is going to trace the circular path. So if it is in anti-clockwise direction, we'll write a phi cap. If it is in clockwise direction, we can represent with minus a phi cap here. Okay, okay, fine. So now here, what is rho here? Rho is nothing but what? Rho is nothing but the normal distance. Yes or no? This is nothing but normal distance from the wire. Normal distance from the current carrying wire. And what is this alpha 2? See, we have considered the current carrying wire of length AB, right? Of length AB. Yes or no? And we try to determine somewhere here. The B field. So the angle subtended by this end, we have considered as alpha 2, and the angle subtended by this end we have considered as alpha 1. Right? Okay. Okay. Yeah. So now, and this alpha 2 and alpha 1 must be always measured. In which direction? Always measured in anti-clockwise direction. In which direction here? In anti-clockwise direction. So that's how we have measured here, right? Okay. Okay. Here. Now see here. Now if you want to apply this formula here, in the problems, okay, how you can apply this? So whenever you are applying the formula in the problems, we have to follow the same conventions. Okay, so that means one end of the wire, this end of the wire is subtending an angle alpha 2. Alpha 2 must be measured in anti-clockwise direction. Other end is subtending an angle alpha 1. Yes or no? Okay, that also has to be measured in anti-clockwise direction. That is the first point. Now if you consider simply a current carrying wire like this, so which end is going to subtend alpha 2 and which end is going to subtend alpha 1? So which one you have to take it as alpha 2 and which end you have to take it as alpha 1. So that is some small confusion students will have. Okay, so for that I will tell you a trick how to consider which end is subtending alpha 2 and which end is subtending alpha 1 here. Now here see here. Now here whatever the convention we have followed, according to this convention we got this result here. The same convention you have to apply whenever you are solving the problems also. Now if you observe here, if you extend this wire here, from this end A, if you extend this wire up to infinity here, if you extend this wire up to infinity, this end, if you extend this end A up to infinity, so as it goes on increases here, what happens to the angle subtended by this end here? As it goes on increases, the angle subtended by this end is going to decrease or not? Yes or no? It is going to decrease. It is going to decrease further, further, further. So if it extends up to infinity here, if this end extends up to infinity, then alpha 2 will tend to what? Alpha 2 will tend to 0. Yes or no? So that means as a tends to infinity, as end a tends to infinity, alpha 2 is tending to what? Alpha 2 is tending to 0. Next, similarly, if you extend this end here, if you extend this end up to infinity in this direction, if you extend this end up to infinity in this direction, then what happens to this angle here? See, if you extend this end further, 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 further like this, always you have to measure what? Always you have to measure the angle in anti-clockwise direction, right? So this will become alpha 1. So as you go on increase further, 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 what will happen here? This alpha 1. So this will become alpha 1. Right. Okay. So what is happening to alpha 1 angle? Alpha 1 is increasing or not? Yes or no? So as you extend this wire, extend this end B to infinity in this direction, so this alpha 1 is going to increase. So if you extend it up to infinity here, if you extend this end up to infinity, alpha 1 will go to what here? Alpha 1 will go to 180 degrees, right? Okay. So here I am writing as end B tends to infinity, then alpha 1 tends to what? Tends to pi or 180 degrees. Okay. So that means if you extend the end of any wire to infinity, okay, as you extend the end of wire to infinity, then if the angle subtended by that end, goes on decreases, then you have to consider it as alpha 2. So we'll simply name it as decreasing angle here. This is for our convenience here. We are representing it as decreasing angle. So what do you mean by decreasing angle here? If you extend the end of the wire to infinity, the angle subtended by that end is going to decrease. So if it is decreasing, then you have to consider that angle as what? That angle as alpha 2. Now similarly, as another end, as end B goes on increases here, as end B tends to infinity, the angle subtended by this end is increasing or not? It is increasing and it is going up to infinity. So I am naming this as increasing angle. See, this terminology is for our convenience here. Okay. So now see here. Now if you are having a current carrying wire like this, now if I ask you what is the B field at this location, then what you can do here? So this end is subtending an angle. Always you have to consider the angle in anti-clockwise direction. So this end is subtending some angle. So always you have to consider the angle in anti-clockwise direction. Now which one you have to take as alpha 2, which one you have to take it as alpha 1. So consider this. See, if you extend this wire here, wire in this direction up to infinity, what happens to this angle here? This angle is going to decrease or not? Yes or no? As this angle is decreasing, we'll consider this as what? We'll consider this as alpha 2. So now if you extend this wire in this direction up to infinity, this angle is increasing. So we'll consider this angle as what? Increasing angle. We'll consider as what? Alpha 1. So now what is the B field at this location here? You can now directly use the formula. So what is the B field? B field is equal to what? Mu I by 4 pi, rho is nothing but normal distance from the wire, Now let us consider the normal distance from the wire from here to here is rho. Let us assume rho only. Okay. So mu I by 4 pi rho into what? You can write simply cos alpha 2. So here let us say alpha 2 is equal to 45 degrees and here alpha 1 is equal to 135 degrees or something. Okay. So you can substitute alpha 2 is equal to 45 degrees here and alpha 1 is equal to, that means you can take any value here depending upon the problem. Okay. No need, we will solve the problem, there it is going to be clear. Okay. So you have to consider this angle as alpha 2 and this angle as alpha 1. Okay. So from the given data you can determine alpha 2 and alpha 1, just substitute in this formula. So we got this formula by using this convention. So if you want to apply this formula, you have to follow the same convention. That is the only rule. Yes or no? Okay. So I hope it is clear here. I hope it is clear. Yes or no here? Is it clear? Yes. Okay. Next. So we are going to apply this formula here. We are going to apply this formula. See here. So we got a finite a current carrying wire of finite length. For this one, the B field we got was what we got here, mu I by 4 pi rho into cos alpha 2 minus cos alpha 1 A phi cap. So this is the formula we got here. This is the formula we got. Okay, rho is the normal distance. Alpha 2 we can call it as increasing angle. So why it is calling as increasing angle, that's what I have explained. Alpha 1 is decreasing angle. Now see here. If suppose this wire extends to infinity here. If suppose this wire extends to infinity. Okay, so as the wire as current carrying wire length tends to infinity, as current carrying wire length tends to infinity. That means if you consider a current carrying wire of infinite length, then what is the B field here? What is the B field? So B field is equal to what? B field is equal to mu I by 4 pi rho. So as both the ends tends to infinity, what will happen here? Alpha 2 will go to what? Alpha 2 will go to 0 degrees, and alpha 1 will go to what? Sorry, I have written. Wait, yeah. Sorry. Here this alpha 2. Sorry, we have considered alpha 2 as decreasing angle, and alpha 1 is increasing angle here. Okay, fine. So mu I by 4 pi rho. So now as this wire tends to infinity here, alpha 2 will go to what? Alpha 2 will go to 0 degrees, because it is decreasing angle. It will go to 0 degrees, and alpha 1 will go to what? Will go to 180 degrees. So cos 0 will become 1, cos 180 will become minus 1, minus of minus will become plus. So plus 1 here, plus 1 here, plus 1, plus 1 you are going to get 2, right? So here you are going to get 2 here, 2 A phi cap. Okay, so here 2 1s, 2 2s. So therefore B field due to a current carrying wire of infinite length, what you got here? Mu I divided by what? Divided by 2 pi rho A phi cap, 2 pi rho A phi cap. Okay, so this is the expression for what here? This is the expression for B field due to a current carrying wire, of infinite length, Okay, so this is the expression we got here. Now similarly, if you are having a current carrying wire which is of the shape circular loop here, let us say the current is flowing around this circular loop. Okay, so the current is flowing around this circular loop. Let us assume it is flowing in anti-clockwise direction. Okay, so this is circular. So current carrying circular loop here, current carrying circular loop. Okay, so let us say this is the center. Now I want to determine the B field exactly at this center here. I want to determine the B field exactly at the center of this current carrying circular loop. Okay, so how we can determine here? See here. Now see here, if I consider a small differential arc length here, I am considering a small differential arc length. So let us say this is d phi. Okay, and let us say the radius is rho, let us assume. So this differential arc length is nothing but what? Is nothing but rho d phi. So the current is flowing like this or not? The current is flowing like this. Okay, so this small differential current element I can consider as what? I can consider as I dl bar, where dl bar is nothing but what? dl bar is nothing but this differential arc length, and this differential arc length is nothing but rho d phi. So its direction is along a phi cap direction. So you can represent this current element as what? I into rho d phi, a phi cap, I into rho d phi a phi cap. So this is the current element I dl bar, right? Okay. Okay, yeah. Okay, so now what is the B field here? What is the B field at the center? So due to a small differential current element, that is due to this small differential current element, what is the B field at the center you are going to get? dB is equal to what? dB is equal to mu I by mu I dl bar cross what? Cross AR cap divided by what? Divided by 4 pi R square. Right. Okay, so here mu into I dl bar is nothing but what? Rho d phi a phi cap cross what? A phi cap cross AR cap. So here let us consider this is rho na. Okay, wait here. Okay, so here you wait. So here you consider simply R here. The distance from the differential current element to the point where you are trying to determine the B field, that we consider as what? We consider as R, and this R has to point in this direction. Always it has to point from the current element to the point where you are trying to find out the B field. Yes or no? So R AR cap here, R AR cap, right? Okay. Okay. So wait, I have done. Okay, see this is R here. Actually this is the radius of circle. Yes or no? Okay, so the radius of circle in general we are going to represent what? We are going to represent in this direction, yes or no? But here AR cap you have to consider in this direction. So I am representing AR cap as what? Minus AR cap, right? Okay, why here? Because in general if you consider a circle here, so this is the radius R. So you are going to represent this R as what? R as R into AR cap, so that is always points from the center to this point, yes or no? But here I am representing the direction opposite to what? Opposite to radius direction. So that's why I am representing it as R into minus AR cap here, R into minus AR cap. Okay. Okay, so that means here you have to write here minus AR cap, okay, divided by what? Divided by 4 pi R square, So what you are going to get here? This is dB. Okay, so this is equal to mu I rho d phi a phi cap cross AR cap here, a phi cap cross minus AR cap. See, in cylindrical coordinate system you are having rho phi z. So in place of rho here we are using R, and here phi, and here z. Just the terminology is changing here. In place of rho we are using here R. Okay, so minus AR cap here. Wait. Here a phi cap, and here this is minus AR cap. So a phi cap cross minus AR cap here, a phi cap cross minus AR cap. What you are going to get here? Here in place of rho we are having R here, that's it. Okay, so a phi cap cross AR cap, a phi cap cross aero cap, you are going to get what? You are going to get minus AZ cap, minus of minus will become plus, so that is you are going to get AZ cap here, divided by 4 pi R square. Okay, See, in cylindrical coordinate system, you are having aero cap, A phi cap, AZ cap here. Now, instead of aero cap, we are using here it as what? R. So that means instead of aero cap, we are representing it with AR cap, and here A phi cap, and here AZ cap, right? Okay, so A phi cap cross AR cap will give you minus AZ cap. A phi cap cross AR cap will give you minus AZ cap. Already here you are having minus, minus of minus will become plus. So that means you are going to get what? You are going to get plus AZ cap, plus AZ cap. Okay, so this is small differential B field here, dB. Right. Okay, so if you want the total B field here, if you want the total B field at the center, what you have to do? What you have to do here? You have to integrate. You have to integrate throughout the circular loop. Yes or no? Okay. Throughout the circular loop. So if you integrate, you are going to get what? You are going to get the total B field. So that is equal to mu I rho d phi by 4 pi r square AZ cap integration with respect to what? Throughout this circular loop. As you move along this circular loop, this phi is going to change. So that means phi is ranging from where to where here? Phi is ranging from 0 to 2 pi. So if you do this, what you are going to get? B is equal to mu I rho by 4 pi r square. So everything is constant with respect to phi or not? Mu is constant, I is constant, rho is constant, 4 pi r square is constant. Yes or no? Okay, so what is left out here? Wait, here in place of rho, what you are using here? R, right? What here? Okay, so here in place of rho, this is R here. Replace everywhere with R. R or rho, everything is same here. Okay, you can represent either with R or rho, it doesn't matter. Okay, so here also you can represent with R. Okay, mu I R integral 0 to 2 pi d phi AZ cap. Now here R will get cancelled here. You are going to get mu I by 4 pi R. Here you are going to get what? Integral d phi is phi. If you substitute the range, you are going to get 2 pi AZ cap. Now here 2 pi 1s, 2 pi 2s. So you are going to get what? You are going to get B field. B field is equal to mu I by 2R. Mu I by 2R AZ cap. So this is the B field direction here. This is the B field. Okay. So this is the B field at the center of what? At the center of circular loop. At the center of current carrying circular loop here. So the B field at the center of circular loop is mu I by 2R. Mu I by 2R, where R is the radius of the circle here. Where R is the radius of the circle. See, you can use either R or you can use what? You can use rho. Okay, anything you can use here. Anything you can use. If you use rho, you are going to get mu I by 2 rho. Yes or no? Okay, so anything you can use, either R or rho. Okay, so if you consider the radius as R, you will use R, or if you consider the radius as rho, you can use rho. So in general, in examinations, they are going to give you in terms of R only. Okay, so that's why I have used R. Right. So R is the radius of the circle here. So this is the B field. This is the B field at the center of the circular loop. Okay. So today we have done the derivations here. We have done the derivations for a current carrying wire. For a current carrying wire carrying the current. For a current carrying wire of finite length. For finite length, what you got here? What you got? A current carrying wire of finite length. What you got? B field. B field is equal to mu I by 4 pi rho into what? Into cos alpha 2 minus cos alpha 1 A phi cap. So this is the expression we got. So if you consider a current carrying wire, of infinite length here, of infinite length. So what we got here? For infinite length, we got B bar is equal to what? Is equal to mu I by 2 pi rho A phi cap. This is the expression we got for current carrying wire of infinite length. This is infinite length here. This is infinite length. right? Okay, next, if you consider a circular loop, of radius rho or r, whatever you want you can take. Okay, if you consider the radius as r, you are going to get what? You are going to get B field, B bar is equal to what? Mu I by what? Mu I by 2r, right? Okay, so what is the direction we got here? We got the direction as what? A z cap. Okay, so this is AR cap, this is AR cap direction, and this is A phi cap direction. Okay, so AR cap cross A phi cap will give you AZ cap direction, that means out of the board. So B field is going to point out of the board, that is in Z direction, right? Okay, so that's what we got here, So these are very important here. These are very important. So most of the questions are based on this formula here. So these three are very important here. Very important. Okay. So all the problems here, all the problems on Biot and Savart's law, most of the problems, 99.99% of the problems will be based on only this formula here. Okay, so we have seen how we got all this formula and all. Okay, so in the next session we are going to apply this formula and we are going to try we try to solve some previous problems. Okay, so I hope it is clear here. See, you just go through the derivation once or twice, then you can easily understand what I have done. Okay, yeah. So these are the formula that we got. Okay, please note it down, all these things here. Okay, so by using this formula, we are going to solve some few problems in the next session here. Okay, so with this I am winding up the session. For today. So tomorrow also at the same time we are going to meet at 4 p.m. here at the same time. Okay, so until then, take care, bye bye.